never straight. It's adjusting continuously. Then that's a direct effect of the way the neurophysiological system works. Now, once you go to the esoteric stressor case, where physical resources are all decks on hand, eyes are where they are, hands are where they should be, but the mind is somewhere else, so to speak, then when the stressor starts applying, you see immediately this left and right automatic handling of the wheel becomes a little bit more intense. And that's a direct effect of the flight syndrome when the stress level goes up. However, it looks like, as you see in the signal here and as you see in the animation, that every stronger rotation to the left automatically is corrected by an equally strong correction to the right and vice versa. So apparently there is a subconscious mechanism in the brain, and we will talk about the hypothesis later on, that does this all the time without being aware of it, as far, of course, as your physical resources are on deck. The problem is when some of these physical resources, your eyes primarily and your hands, are distracted, what happens? And that's the case with sensory motor stressors, like texting while driving. Then what happens is, and you will see this the system still, this automatic correction system still tries to work, but because the loop breaks, momentarily is left unable to do the correction, the automatic correction, and that creates the lane deviation. So, what's the takeaway from this? Stressors looks like they all have the same immediate effect. They create flight responses. These responses percolate to whatever they can percolate, which is your arms in this case. And they create this very distinct, intensified pattern, which your brain, through most likely a mechanism that is called anterior cingulate cortex, which is part of the brain that is known, that is trying to correct conflict, most likely. This is a hypothesis, but certainly some part of the brain does an excellent job in correcting this, as far as it can use the physical resources for this, which is your eye-hand feedback loop. Once this feedback loop is interrupted, and that's the case with sensory motor stressors, then momentarily this mechanism fails. And that's when everything goes south, so to speak. So what does this mean? Are you okay if you are esoterically abstracted? Does this mechanism keep you safe? Immediately, yes. Potentially, no. And I would say don't reach for the glove in this case, glove box. Because already the steering pattern you have is quite intensified due to the flight effect. Therefore, even a small distraction will leave this uncorrected. Depending on your speed, this uncorrection will result maybe into major lane deviation. So it's like the effect of, I would say, a pressure cooker. As far as the lid is on, you are okay. But if the lid goes out, because there is already a lot of pressure in the system, it will blow up. Unfortunately, that's all the time I had. Thank you very much. And we'll discuss it.
So while we're changing, if we had more time, we'd talk about what we actually did to start detecting those levels of stress and doing something about it. And we did an intervention study. And I also want to add that we went beyond the simulator. We went to the test track and verified our results out on the test track as well in an actual automobile, a production automobile. Our next speaker is Sulban Park, who is a research engineer with the Autonomous Vehicle Research Section of Mobis North America. Now, it turns out that Sulban and I met on the phone earlier this year, and we decided that we look different in person than we did on the phone. But I think we're ready, and please welcome Sobhan, who has also come from Michigan, but had a much easier time of it than John.
Hi everyone. I hope everyone is off to a great start of the conference. I would like to thank the host for having me as part of the panel for this breakout session. And today I'd like to talk about driver intention and state estimation. I am a research engineer from MOBIS, Technical Center of North America. My focus is in human-machine interface of autonomous vehicles. And I would like to insert a disclaimer here. I don't have any graphs or results to show because of the product that we are currently in development. We plan to go public soon, and I couldn't include those. And our group is very young. But before going into those, I thought I bet a lot of people haven't heard of MOBIS before, and I thought this is a fitting introduction to go with. And we are part of Hyundai Motor Group, which is our parent company. And under their group, there's Hyundai Motor Company and Kia Motors, and there's us and many other. A lot of people get us confused for Hyundai, but we're not a Hyundai. We're a tier 1 supplier in Hyundai, Kia, and OEM. Although we're under the same group, we don't exclusive work for these OEMs. We do work with other OEMs, including GM, Chrysler, and et cetera. And how are we doing in the industry? According to Automotive News, published on June 20th, 2016, they ranked tier 1 suppliers by sales of original equipment parts in 2015, and we ranked 6th. So I think it's safe to say we aren't doing too bad. And where are we located? We are in Plymouth, Michigan, but our headquarters is in South Korea. They've been around for a long time, but they entered North American market very recently. I would say around 5 years or so. But my very group, which is focused in autonomous vehicle, this group just started about a year ago, and that's when I joined the group. And we do have other technical centers focused on many different things in Germany, India, and China. And with that said, people say a picture is worth 1,000 words, and this video that I'm about to show is probably worth 1,000 words times the frames, however many frames in this video. And this video is what we showcased at CES 2017 earlier in January, and we had 3 different scenarios. It was set up with this snazzy demo vehicle embedded with sensors. It was supposed to be an immersive experience for the visitors, and there are a couple of different scenarios, and this one is about healthcare, and I think this shows what MOBIS visions lie when we develop this level 4 autonomy safety product. So I hope you guys can sit back and enjoy the ride.
Please look straight ahead. Driver certification completed. Welcome, Mr. Moby. Adjusting seat positioning, mirror, and air conditioning for your convenience. You have an appointment at 1 p.m. Would you like a route guide to Aries Restaurant? The total driving time will be an hour, with an estimated time of arrival at 12:40. How are you feeling today? Hold on a second. Collecting biodata. Looks like you are in good health condition. No charging infra on the way to destination. Switching to energy-saving driving mode. Warning, falling rock area ahead.
Autonomous Driving Vehicle by Mobis is designed to handle all kinds of unexpected situations on the road. Sensors detect obstacles and calculate their distances from your vehicle. V2V system warned other car around. And car fully control brake and steering wheel to keep drivers safe from unexpected situation. Ultrasonic sensors. Side camera. Front radar. Corner radars. Laser scanner. Camera. V2X antenna. These are the sensors that enables your vehicle to cover a 360-degree field of view around it and makes it awake all the time.
Abnormal heart rate detected. Calling family doctor. Switching to autonomous driving mode and initiating relax mode. Take a deep breath and relax. Traffic jam ahead. Rerouting. Heart rate became stable. You have arrived at Aries Restaurant. Updating parking space information. Basement's second floor A22 has reserved for you. Would you like to park autonomously? Your vehicle will be parked at A22. Mobis enriches driving experience and offers healthcare services to drivers.
That was a little heartwarming clip right there, but I hope this gives you guys a good idea of what you're working on. But although I would have to say some of the HMI concepts of control transfers and such, that is still a topic of research for us. It is, some of those are, so take it with a grain of salt because those are shown as a concept at the show. And nextly, I'd like to, so this was the demo vehicle we had at the CES. I put it in there for illustration purposes, but we are at NTCA. For our department, we're building the HMI lab, Human Machine Interface Lab, with the high fidelity motion-based driving simulators, because we would like to validate a lot of human factors theories that is of high interest for Mobis. and also test our algorithms and sensors before taking out, and how humans interact with them before taking out on the roads and tracks. And so about L4, it is an ecosystem: car, the driver, and the road. That's how the driving works. You have to reach, all these agents have to reach an equilibrium to work as a safe agent on the road. And when we think about L4, we usually imagine us getting in the car taking us where we want to be without us worrying about what the road is like, not even looking at it, doing our own thing in the car. But until we reach that level, I think it's going to take some time because the infrastructure has to get ready, and the market has to be penetrated by the autonomous vehicles and all that. So while we are getting there, what Mobis would like to do is making a safe transition. When our L4 product is deployed, we want to put a product out there that is going to benefit the society the most in terms of safer mobility. And so for us to do that, we've been working with a few research institutes in America to look at statistics and databases to really figure out where we can, identify those features. So we look at how the accidents happen, why they happen, who are causing it, where it happened, and et cetera. And we are facilitating our development with those research efforts. And so with that, I would like to go over our overall approaches and perspectives, how we approach this issue of human-machine interface. Nice little fitting photo for the human factors breakout session. I thought vehicle made out of little humans. There are many channels through which we can analyze a driver and make a good estimation of driver intention and state. A good example would be a steering wheel and the pedals and some other vehicle signals, including the turn signals and vehicle speed and acceleration, through which you can make a good context out of to estimate the driver's state and intention. And if you have implemented the cameras in the front of the vehicle and the rear of the vehicle, or for the driver, you'll be able to reinforce the context that you're making the estimation out of even further. And there's a little mystery sensor in there that you can implement that we are working on. But a good example of those mystery sensors would be the heart rate sensor that was shown earlier in the video. So when humans, we can collect many signals from the humans. And when we, as a tier 1, when we look at this problem, what we think about is establishing a good correlation. We want to find the correlation between the signals that comes out of the human and the characteristics of the humans. And we want to find the usable signals that will give us good confidence in making an estimation on the human driver estimate and state. And also, we want to build a sensor that is robust, but not intrusive in the vehicle setting, which is easier said than done. So those are the approaches we're taking, but also we are taking active efforts into ensuring security and privacy issues when we are collecting these signals. But we are preparing those in technical sides of things, but I think the discussion between the consumers, OEMs, tier 1s, and the governments will have to come together to establish a common ground when we deal with these signals to further reinforce the L4 technologies. So we would also like to trace back the signals back to the humans to make a good judgment, to help the vehicle make a good decision when it's making autonomously driving decisions. And when we do that, the problems you usually run into, although there's a good correlation established between such signals and certain driver characteristics, there are many variances between subjects, and to overcome those, we are working on an algorithm that can be adapted, and which means and also establishes different thresholds for different people, and also can better recognize the patterns in those signals. So I think that wraps up my presentation. There's more to come from Mobis, and I hope to share more things with solid product in the future with you guys. Thanks for listening.
I don't know about you, but I was really disappointed to hear that that wasn't available because I was ready to trade in the F-250 for the car that let me lay back and chill out. So our final speaker is Shan Bao. She is Assistant Research Scientist at the University of Associate. That's a very important thing. I stand corrected. She is associate, and I think that's kind of a new thing. Right? Yes, it is. So she got a promotion. So give her a hand. And I can tell you that it was well deserved because I've had the privilege of working with Shan for the last 3 years on another aspect of this same research, where she was really looking at some naturalistic driving data and how driver behavior influences certain things. So she's with the University of Michigan Transportation Research Institute, and we've already congratulated her. So Shan, it's all yours.
Thank you, Robert. Howdy and good morning. How's everybody doing? Okay, so my name is Shan Bao, and thank you, Robert, for the nice introduction. And as Robert mentioned, the past 3 years, I have had the great honor to join Robert's team to work on the exciting Toyota project that we have awesome findings and results, but due to the time constraints today, and also I want to give Robert another reason to invite me back to the awesome place and great weather. So today, actually, I'm going to talk another study which is directly related to drivers' interaction with automated vehicle technologies. So the title is An Investigation of Drivers' Adaptation Behavior when Interacting with Connected and Automated Vehicle Technologies. So the objective is pretty self-explanatory. So we have several main concepts here: driver adaptation, connected and automated vehicle technologies. So the first question to be addressed is, what is driver adaptation behavior? So in this study, it refers to drivers change their behavior adaptively as they integrate these new supporting systems into their driving routines. So there are several points we need to make sure. The first one is the safety consequences. So we want to make sure when drivers interacting with these new safety systems, we want to promote the positive safety consequences while to reduce the negative safety consequences. Another thing is that how long typically does it take for drivers, especially different group of drivers, to adapt to those systems? So the third thing we need to make sure is that what is the individual differences going to play a role in this kind of study. So this research, we are aiming to do 3 main tasks. The first is we're going to develop some behavior measurements metrics so we can quantify driving styles. Then we're going to use these measurements to see how different technologies like connected and automated vehicle technologies are going to change drivers' driving styles. So this study is basically a data-driven study. So we use the 3 large scale of existing arbitrarily collected naturalistic driving study data sets. One is on the level 1 automated vehicle technologies, which is adaptive cruise control system. It's from the ACAS, which is abbreviation for the Advanced Crash Avoidance System, FOT study. The second data set is coming from the Integrated Vehicle-Based Safety System, FOT study. The third data set we use is from the Safety Pilot FOT study, which is, in the world, it is the largest data set on connected vehicle technologies. So we want to see how drivers' driving styles would change with those different technologies. So for the first part, we want to look at how their driving style can be measured and quantified. So in this concept, we extracted the data from the ACAS data to look at how drivers' following behavior when they are driving on the highways. So in the ACAS data, originally we had 66 drivers. Each driver was driving the instrumented vehicle for 4 weeks. The first week we call the baseline, which is all the system function. So the ACC function was not presented to the drivers. However, they still get access to the conventional cruise control, so which is, can be used as the baseline. So in the following 3 weeks, the ACC system was presented to the driver. Also, the drivers were encouraged but not forced to use the ACC system. So we used their longitudinal control behavior, including their acceleration, speeding, tailgating, to identify the metrics. Then we quantify, and using the PCA, principal component analysis, and a cluster analysis method to classify the drivers into 3 groups. One is called risky driver, high risky driver. The second is moderate risky driver. The third one is the low risky driver. So we want to see how those 3 groups of drivers would interact with these ACC systems. So originally we had, as I mentioned, had 66 drivers, but to fall into the criteria we have for the highway driving following events, we have certain criteria, like they have to have a certain duration period when they're driving on the highway while following other vehicles, and also they have a certain closing speed from the following vehicle. So from the 66, we actually had 52 drivers qualified with the qualified data. So the 52 drivers, actually there are 24 female and 28 males. So in the high-risk group, actually you can see there is about 5 drivers with relatively more young drivers, with, while there is no older drivers following into that category, which is consistent with the literature and our previous studies. So also, if you can see, so this high-risk group, you can see that their closing speed and also their driving speed kind of following into the lower level of the right quarter. That means they are spending a lot of time tailgating and also driving at a high speed, while the other 2 groups, their closing speed, following behavior actually more spread out, relatively speaking. So as a validation method, we also look at, okay, so we have all these 50 drivers classified into 3 groups. So we also need to validate if our methodology makes sense. So we also look at, okay, so what is, how these 3 groups of drivers doing in terms of, do they have large proportion of hard braking events, which is, you can see here, this blue pie actually represents the risky, high-risky driver group. So they actually dominate all the hard braking events, which is defined about 0.3G here. You can imagine on the highway driving, the 0.3G deceleration actually is kind of rare. So also the high-risky driver group also has a relatively, and also statistically more significant proportion of time tailgating other vehicles, and also speeding ratio, and also this one is the short TTC. So these methods actually validate our algorithm of behavior measurement metrics, saying our algorithm can actually accurately classify drivers into different groups. So next, we want to say, after we classify drivers into different groups, how they're going to do in terms of interacting with the ACC system. So as you can see here, this picture shows we have found a very interesting interaction effect between the risky group and also the system use. So as I mentioned, each driver was driving an instrumented vehicle for 4 weeks. The first week we call baseline, so with the conventional cruise control system. So during the following 3 weeks, we call treatment condition, which is the ACC was provided but not forced them to use, but they are encouraged to use. So as you can see here, for the high risky driver, during the baseline condition, their risky score is very, very high. It's the highest among all the drivers. But during the treatment condition, the 3 weeks, when the ACC was on, their driving risky score was significantly reduced. And even during the treatment condition, when the ACC was not activated, their risky score was also significantly reduced. So there's no such significant differences observed for moderate risk group and also low risk group. So that suggests something. So that means that the ACC use can actually provide more safety benefits for high-risky drivers, even they are not using the ACC by optional. So we also observe some gender-related differences. So relatively speaking, male drivers were more risky than female drivers. We also observed age-related differences that, relatively speaking, not surprising. Younger drivers were more risky when compared to middle-aged and older drivers. So I think for our industry development of a connected and automated, the user was happy with it. So in this engagement rate as a surrogate for user provided to them, but now they were not forced to use them, only they were encouraged to use them. So we want to measure how drivers would voluntarily to use the AC system. So as you can see here, during the first week, this is the conventional cruise control use rate. So during the second week, when ACC was provided, so there is a increased use of the ACC system. However, during the third week, there is a drop, but during the last week, the ACC use rate was also significantly increased. So this tells us what? So this tells us several information. So first is that it takes several weeks at least for drivers to get used to the system. So at the first week, they were, first week of the treatment condition, they were introduced to the ACC system, so they were curious about it. So there is an increased use rate. But during the second week of the treatment condition, drivers say, hey, maybe I don't want to use that much. Maybe I want to be more cautious about it. So there is a drop. But during the last week of their participation, there is a significant increase of the ACC use rate. So when we took another close look at the data, that we also found that there are some interesting age and gender-related differences. So these yellow lines stand for the older drivers of ACC use. As you can see, their ACC use rate actually pretty steady increased across the time when compared to the other groups. So that suggests something, that older drivers, relatively speaking, they have more trust and rely on the system relatively when compared to the middle-aged and younger drivers. So also we found some interesting gender-related differences. So for male drivers, their ACC use rate has relatively been steady, while the female drivers had some doubts, concerns at the beginning, but it also increased later on. So for the second part of the study, we look at how the radar-based crash warning system or the impact on drivers' following behavior. So the data we used was from the integrated vehicle-based safety system. So the original study was funded by US DOT. Then we have collected this huge data set. So in that study, we had a total of about 108 drivers participated in the study. So there was total 16 instrumented research vehicles with 7 radars and different camera views. We captured 500 more data channels with 4 camera views. So every driver was driving the vehicle for 6 weeks. The first 2 weeks we called baseline, which is the warning system was muted while still functioning at the background. So the following 4 weeks we call treatment condition, while all the warning systems were presented to the drivers, including the forward crash warning systems. So using the same definition of steady-state highway car following events, we have the average speed, range rate. We also extracted the IVBSS data to develop a highway following events data table. So 83 drivers qualified. So this is the distribution in terms of gender, age, and also whether they wear glasses. So again, using the same PCA and cluster analysis, we divided all the 83 drivers into three risky groups: aggressive, normal, conservative, to see whether the crash warning system will change their driving behavior, whether their gender, whether they wear glasses will impact on their following behavior. So we have observed significant age-related differences that relatively speaking, younger drivers was relatively the most risky driving group. However, we didn't find the significant impact from the radar-based crash warning system in terms of increasing drivers getting more conservative or more risky. So that not necessarily be a bad thing, because we don't want the drivers. So there was a concern whether maybe drivers would more rely on the warning system, so they may be more likely to engage in the tailgating behavior. So our study didn't find that result. So the third part of analysis, what we used data was from the safety pilot data. As I mentioned, it is the world's largest data set on connected vehicle technologies. So it is also a crash warning system. For the longitudinal speaking, there is FCW and also EBL, which is the emergency braking light warning systems. So at the peak time, we had 3,000 vehicles running in the Ann Arbor, southeast of Michigan area, equipped with all those DSRC devices. Among those 3,000 vehicles, we had 140 fully instrumented vehicles with the DAS. So we have vehicle kinematic features and different camera views, just as the previous studies. So out of the 140 fully instrumented vehicles, we have collected 2.5 million of data, miles of driving data. So again, we use the same definition for the steady-state highway car following definition. We extracted the data. So different from the IVBSS data set, we had the baseline. So for the safety pilot data, on the first day when drivers were participating in the study, all the warning functions were presented. So there is really no baseline or treatment differences. However, we want to know if drivers were exposed to the system longer, whether their following behavior would change. So what we did is that for each driver, we look at the very first 50 following events. Then we look in the middle 50 of their following events. Typically, it's like 1 year into their participation. Then also the last 50 following events for each driver, we compare their driving scores, driving styles, to see if those different exposure time will play a different in their scores. So similar to the IVBSS study analysis, we did not find statistical significance, which is, again, not necessarily be a bad thing, because we did not find that drivers would be more risky with the crash warning systems. So in this study, again, so we have done several work. First is we have developed a driver quantification behavior-based metrics. So that has been validated as a pretty effective way to quantify and measure driving styles. And we also look at a different advanced vehicle safety system to see whether that's going to change drivers' following behavior. So the conclusion is, when compared to the automated vehicle features, the warning system may not be as effective as the ACC system to change drivers' following behavior. We also observed that it takes several weeks at least for a certain group of drivers to get used to the new systems. So there is also significant individual differences, including age. That older drivers were more likely to use the AC system when compared to other age groups, and the females, there are some concerns when compared to the male drivers. So I think that's my basic presentation today, and we'll have questions. Thank you very much.
Thank you so much. We're checking about whether or not we have some time to look at this. I will say that one of the things that pointed out is consistent with some research that we're doing here in Texas on over-representation, particularly among young male drivers. And they show up in the crash statistics, they show up in the research. And if we can do systems that actually work for that group, we have a real chance. Does anyone, okay, they're telling us, I'm sure you'll want to speak to these people during the conference. Let's thank them again for the great work that they've done. Thank you. No questions. Oh, hey, Bill, you're sitting up